Welcome to my presentation on G-DexGrasp, generalizable dexterous grasping synthesis via path-aware prior retrieval and prior-assisted generation. This work is a collaborative effort among Shenzhen University, Dalian University of Technology, Shandong University, and Shenyang University of Technology. What we aim to achieve is to make robots work more like humans, enabling them to carry out various tasks independently. To do this, there are two key things we need to focus on. First, the robot should be able to use dexterous hands with many degrees of freedom to perform tasks correctly and stably. Second, if we want robots to really work like humans, they also need to understand our behaviors and intentions during interaction. In the past, much work on dexterous or human hand grasping focused on general tasks, mainly ensuring stable grasps and avoiding penetration. However, these approaches often lack semantic understanding. Some task-oriented methods do incorporate object functionalities or semantic cues, allowing different grasps for the same object, but their labels are usually predefined and cannot handle unstructured language. Recently, language-guided grasp generation has emerged, yet these methods still face limited generalization. The generalization ability of these methods is limited mainly due to three factors: the diversity and complexity of real-world objects, the unstructured nature of language, and the difficulty of collecting gestures that are human-like, physically feasible, and semantically consistent. These challenges fundamentally constrain data-driven synthesis of semantic dexterous grasps. Therefore, we propose G-DexGrasp, which leverages an enhanced retrieval mechanism to incorporate priors into the grasp synthesis process, thereby reducing the dependence on large-scale semantic grasping datasets. Our pipeline consists of three main components: generalizable prior retrieval, path-aware grasp generation, prior-guided grasp optimization, and given three types of input: a 3D object, its rendered views, and a task instruction. We first built a prior dataset by clustering a thought pose based on object parts, grasp types, and hand poses. Given the task instruction and object images, we infer the target object part and grasp type, and the part is extracted from 2D mask and projected to 3D space. Then, using part grasp similarity, we retrieve hand joint and contact information from the database. Next, by leveraging the 3D part priors and hand pose priors, we first center the grasp around the target part and also condition on some global object features. Then, using a conditional VAE, we train on the existing dataset to generate the hand's overall translation and rotation. Finally, combined with the retrieved joint priors, this gives us an initial grasp pose. Naturally, these initial grasps are neither perfect nor fully physically feasible. To address this, we introduce a two-stage grasp pose optimization process that leverages the retrieved hand contact distribution priors and part priors. As a result, the grasp becomes more physically feasible, with reduced penetration and better contact enforcement. For our experiments, we trained CV on a thought pose dataset, and collected a new test dataset containing over 300 novel objects across more than 30 categories. We found that our method generalizes better across many of these new object categories. We also ran some comparisons and ablation experiments, which clearly show that our method works well and is practically feasible. Thank you all for your attention.